Hello, Royals. Let's talk about lesson 1.11 and the number of roots. It's another lesson where students get a tool like the quadratic formula called the discriminant, and then they sometimes use it in the wrong spots. I want to talk about a question right from the lesson that I hope we had a chance to look at. We're asked to determine the number of x-intercepts for this quadratic function. Sometimes students see number of x-intercepts and they think discriminant. And discriminant is great because from standard form, it tells you how many x-intercepts you have. But we're not in standard form. In class, we hopefully had a chance to quickly talk about how g is a quadratic function that's been vertically reflected, stretched vertically by 1/2, translated right 3/4, and down 5/7. So it has we can communicate this. G has a negative maximum. Or I could point out on my sketch and say, notice that G's vertex is below the x-axis, and G opens down. And for either one of these reasons, I should be able to say, look, G has no x-intercepts. And that should be very, very easy for us to do, even with fractional values here. Like having a vertex that's shifted right 3/4 and down 5/7 does not make this question any harder. It would make the question harder to get this into standard form. Now, this is something I normally don't take the time to do in class because it's so inefficient, but I really want to drive the point here. A student who says, okie doke, I'm going to get this to standard form. So I'm going to multiply this out, and that'll be, well, you know what? I might actually want to write that out twice. That's going to take me a little bit longer and take a little bit more space, but I know this will get me the right answer. I'll do x squared minus 3/4 x minus 3/4 x. That's minus 6/4 x. I'm going to reduce that to minus 3/2 x. And then negative 3/4 times negative 3/4, that's positive 9/16, minus 5/7. If a student doesn't know their fraction facts, then they're reaching for a calculator already here, which is going to slow them down. Let's see, then we multiply through by negative 1/2 to get negative 1/2 x squared plus 3/4 x minus 9/32 minus 5/7. And then, oh no, I need to find a common denominator between 32 and 7. And 7's a prime number, so I know 32 doesn't have any shared factors with it. That means I'm pretty sure that the lowest common denominator is actually their product. This is going to be a mess. Plus 3/4 x minus, what is that, 63? Oh boy, 32 times 7 is going to be 14, 21, 22, 224ths. Minus, it's going to be 320, 160, 224ths. I'm going to probably have to grab a calculator to check this work. X squared plus 3/4 x. Now, imagine how much space I would give you for this question. I don't think you need a lot of space to draw a sketch and convince me that there has no x-intercept. And look at how much space I'm using here, which is, once again, why I would be concerned if a student is asking for more space. The amount of space that I give you on a test should be indicative of how much space you should need, and the amount of time that I budget for a test should be indicative of how much time it should need. I've said this before, different students process at different speeds, but a student who chooses to do this should not get extra time because they're making a bad choice. They're not demonstrating an understanding of key ideas. I'm just kind of stubborn, so I still want to show that this should work. Although, again, give me a sec here to check my calculations. Negative 9/32 minus 5/7 is negative 223, 224. It's cool. So now that I'm in standard form, finally I can use my discriminant. I communicate that I'm doing my discriminant, b squared minus 4ac. Make sure you label or announce this, even in an inefficient solution. That's going to be 3/4 squared minus 4 times negative 1/2 times negative 223, 224ths. So my discriminant is going to be 9/16. Let's start simplifying here. I guess that'll be plus 2 times negative 223, 224ths. And then I can simplify that a little bit to get 9/16 minus 223 112ths. I'm pretty sure that there's a common denominator here. You know what? I'm getting a little tired of this inefficient solution, so I will just reach for my calculator. Over 112. Maybe I could try to convince my reader that this is actually negative, but you should show me your negative discriminant and then say, oh, look, this is less than 0, therefore there's no x-intercepts. Once again, this student would not, I mean, there's different ways of arguing this. You could say a student that did this has just eaten up their time and space that they should be using on another question. So maybe they won't have a chance to finish questions, and that's, I think they've earned that. I think they deserve what happens there. Now, normally, if a student then is allowed extra time because they've chosen inefficient methods, this solution would not get full marks because it demonstrates a misunderstanding of when the discriminant is useful, and it demonstrates a misunderstanding of transformations of quadratics as well. This is completely inefficient. And we are looking for efficient solutions, not necessarily fast solutions, but efficient solutions. Okay. Let's try another example, kind of like the one in class. I just changed one little thing that makes it a little bit more interesting. It's one of those K-type questions, students sometimes call them. Let's see, the function f of x equals negative 2x squared plus 3kx plus k has only one x-intercept. Let's find the values of k. So this function is in standard form, and in standard form, I'm having a hard time seeing. I know that it opens down. I may be able to predict. I think I can see one value of k that would make sure that this has only one x-intercept, but I'm expected to present a well-communicated solution as well. And I'm pretty sure there's another solution. I'm always worried about when there's, or let's say warning bells go off when I see a plural in the directions. That should remind me that there may be the chance for more than one solution. So in this case, because this is in standard form and I'm told that the function only has one x-intercept, the use of the discriminant is probably the most efficient way. I know that if a function is only going to have one x-intercept, that my discriminant is going to equal 0. Again, I'm expected to communicate that fact. So I'm going to set my discriminant equal to 0. That means that b squared minus 4ac is going to equal to 0. Now just be careful here because a lot of people think that b is 3. Now b is the coefficient of the x term, which is unknown in this case. It's going to be 3 times k, or 3k. So my b value is 3k, and then also be careful, make sure that you're squaring 3k. You're not doing 3 times the square of k, you're doing the square of 3 times k. A is negative 2, and C is k. All right? Now, this is an equation that has an unknown in it that I should be able to solve, but let's tidy it up a bit. I'm not really recognizing it right now. I'll square 3k, which means 3k times 3k, which is 3 times 3 times k, or 3 squared times k squared, or 9k squared. I'll do a negative 4 times negative 2 times a k, which will be a positive 8 multiplied by a k. And then at this point, we discussed it in class as well, but on tests and quizzes, students often struggle here. I think it's just because they don't see an x. So they don't recognize that this is an equation with 2 instances of an unknown with an exponent of 2. That's called a quadratic equation. Do not try to solve this equation by subtracting 8k and then dividing both sides by k. You can't divide by unknowns. You don't know what it is. It might be 0. We solve quadratic equations by either using the quadratic formula. Well, this is binomial, so I don't think I need to do that. Completing the square. Yeah, no thanks. The coefficients are a mess. Or by factoring. In fact, I think I probably should have put this up top, because solving by factoring is super fast when it works. And the first type of factoring that I should always check for is common factoring first. And I see a common factor of k, leaving me with a quotient of 9k plus 8. Now I have this equation written as a product. And the only way that the multiplication of two things can equal 0 is if the first thing is equal to 0 or the second thing is equal to 0. And that gives me two little linear equations that I can solve very, let's say, efficiently instead of quickly. Like that. Sorry. Those are the two values of k. That will make sure that this has only one x-intercept. Now, I showed a different solution in class to, or I usually get around to showing a different solution in class where we find an expression for the axis of symmetry using x equals negative b over 2a, and then set our optimal value equal to 0. I want to show the approach of solving this one by completing the square, but I think it'll illustrate that in this case, solving by completing the square is not the most efficient approach. So let me just copy this down here. We've got negative 2x squared plus 3kx plus k. And if there's only one x-intercept here, I think I'm working more sort of visually. That means that whether it's on this side or this side, I'm not so sure. That means that my optimal value must be 0. So that's going to be my strategy to this approach. I'm going to find an expression for the optimal value, and I'm going to set it equal to 0. I still think that the vertex express shortcut, the axis of symmetry formula, will get you to an expression for the optimal value faster. But let's try this by completing the square, because I want to show you some algebraic completing the square. Not a great idea, but it should work. So completing the square, I need a monic trinomial there. I'll remove a factor of negative 2, 3k. If I remove a factor of negative 2, leaves me with negative 3 halves k x. Then I'm going to complete the square. X squared minus 3 halves k x. I'm going to have to add something and subtract it to complete that square. Maybe over here, I'll sketch in my square. As x squared, negative 3 halves k needs to be split evenly into negative 3/4 k and negative 3/4 k x and x. That means that this is x minus 3/4 and x minus 3/4. That means that this square right here, 3/4 k. This square right here is going to have dimensions negative 3/4 k by negative 3/4 k, which means it's going to be 9/16 k squared. I told you it wasn't going to be the most efficient approach. All right, let's factor this, which I don't actually need to do in this question because I only need to find an expression for the optimal value, but maybe I'm not that clever. Maybe I don't realize that. There's my square of area x minus 3/4. Okay, yeah. Right. Sorry, I wasn't sure if I was supposed to put the k in there. I do. I need it. If I forget it, it's not going to affect my answer though. Minus 9/16 k squared plus k. I'm going to distribute my negative 2 through. That'll give me negative 2 x minus 3/4 k. That should be up top in the numerator. Negative 2 times negative 9/16. So I'm going to simplify the 2 and the 16 down to positive 9/8 k squared plus k. And reminding myself that my optimal value must be 0. This means that I'm going to set 9/8 k squared plus k equal to 0. Now with equations, if I want to eliminate fractions, I'm allowed to. So I'm just going to multiply both sides of this equation by 8, and that'll give me 9k squared plus 8k equals 0. And I'll leave you from here because at this point, we have the same equation that we had in our previous approach. Okay, but look at the amount of space that it took to get here. It was basically 1, 2, 3 lines versus this mess. Okay. Not an efficient approach. I'd be kind of impressed if a student could do that, but that doesn't mean that it was still the right choice, right? Like you could watch someone do a backflip off of a roof and that'd be impressive, but that still wasn't the right choice. So look for efficient solutions.